In this episode, we're going to connect quality assurance testing to real operational outcomes. Because testing is not a box you check, it is a control system that decides whether change is safe to release. Beginners often imagine testing as running a few checks and hoping the results are representative. But in operational environments, the purpose of testing is to reduce uncertainty in specific ways. Load testing reduces uncertainty about performance under expected and unexpected demand. Regression testing reduces uncertainty about whether a change broke something that used to work. Integration testing reduces uncertainty about whether components that depend on each other can still cooperate correctly. When these strategies are operationalized, they are not occasional events. They become repeatable pipeline behaviors with clear triggers, clear acceptance criteria, and clear interpretation rules. The goal here is to understand what each strategy is, why it matters in the real world, and how to fit them together so the pipeline catches the right problems without becoming slow, noisy, or untrusted. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Load testing is about understanding how a system behaves when it is asked to do a lot of work, and that can mean high traffic, many concurrent users, or heavy data processing. A beginner misunderstanding is to think load testing exists only to find the maximum number the system can handle before it falls over. Operators care about that limit, but they care even more about the shape of behavior as demand increases, because that shape reveals bottlenecks and failure modes. A healthy system should degrade predictably, meaning it might slow down gradually or shed non-critical work, rather than failing suddenly and unpredictably. Load testing also helps validate assumptions about capacity planning and auto-scaling behavior, which matters because automation often changes the performance profile of services over time. Another practical value is that load tests can expose timeouts, resource leaks, and queue buildup that functional tests never detect. When you operationalize load testing, you treat it as a measurement tool that provides evidence about latency, error rates, and resource usage under stress. That evidence helps you decide whether a release is safe for real traffic conditions rather than just safe in an ideal lab. Operationalizing load testing also means being thoughtful about when and where you run it, because heavy tests can be disruptive and expensive. If you run a large load test on every small change, you may slow down delivery and overload shared environments, which creates frustration and encourages bypass behavior. Operators therefore choose a strategy that balances confidence with cost, such as running smaller performance checks frequently and larger stress tests on schedules or before major releases. The key is that load testing should be representative, meaning it should use realistic request patterns and realistic data flows, because unrealistic tests can produce misleading confidence. It also means defining clear success criteria, such as acceptable latency ranges and acceptable error thresholds, because without those criteria, load tests become vague graphs that teams interpret differently. Another operator habit is to treat performance regressions as failures of quality, not as mere inconvenience, because slow systems can be as harmful as broken systems. When load testing is integrated with clear thresholds and stable execution, it becomes a reliable part of release decision-making. Regression testing is about preserving known good behavior as you change a system, and that makes it one of the most important forms of operational protection. A regression is when something that used to work stops working due to a change, and regressions are common because complex systems have hidden dependencies and edge cases. Beginners sometimes think regressions happen only when a developer makes a mistake, but regressions can also come from dependency updates, configuration changes, or environmental drift. Regression tests create a safety net by continuously checking that critical behaviors still hold after each change. The operational value is that regressions are easier and cheaper to fix when you catch them close to the change that introduced them. If you catch a regression weeks later, the system has changed many times, and it becomes harder to identify the cause and harder to roll back safely. When you operationalize regression testing, you define what behaviors are essential, and you check them consistently, with stable results that teams can trust. Trust matters because if regression tests are flaky, people stop respecting them, and the safety net breaks. Regression testing also benefits from careful scope design because not every regression test needs to run on every change. Some regressions are likely only when a specific part of the codebase changes, and some are important enough that they should always run. Operators often treat regression suites as layered, with a core set that runs frequently and a broader set that runs less frequently, but still regularly. The operator mindset is to focus core regression tests on user-critical paths and on past failure patterns, because those are the areas where regressions are most costly. Another important point is that regression tests should be deterministic, meaning they produce the same result when run in the same conditions, because non-deterministic tests create confusion. When tests depend on time, random values, or external services, they can become flaky, and flakiness is a major operational tax. Operationalizing regression testing, therefore, includes designing tests that are stable and designing environments that support stability. Even as a beginner, you can appreciate that a test that sometimes fails without reason is worse than no test, because it trains the team to ignore warnings. Integration testing focuses on whether multiple components work together, which is essential because many failures occur at boundaries rather than inside individual components. A service might work perfectly in isolation and still fail in the real environment because it cannot authenticate to another service, cannot parse the other service's response, or cannot tolerate the other service's latency. Integration tests are designed to exercise those interactions in controlled conditions, proving that contracts between components still hold. For beginners, a contract is simply an agreement about inputs and outputs, such as what a request looks like and what a response contains. When contracts change without coordination, integrations break, and those breaks are among the most expensive failures because they often affect multiple teams and multiple systems. Operationalizing integration testing means deciding which interactions are critical and then creating repeatable tests that validate those interactions under realistic configurations. It also means keeping those tests close enough to production behavior that they catch meaningful issues without requiring full production traffic. Integration tests are the bridge between unit-level confidence and system-level confidence. Integration testing also introduces a common operational tension. The more realistic the integration environment, the more complex it becomes, and complexity can lead to instability. If integration tests depend on many external systems that are themselves changing, tests can become flaky due to factors unrelated to the change under test. Operators address this by controlling the integration environment as much as possible, stabilizing dependencies, and using mocks or stubs selectively for components that cannot be reliably included. A beginner might see mocks as cheating, but operators see them as tools that reduce noise when full integration is impractical. The key is to be honest about what an integration test proves, because a test that uses a stub proves that your component behaves correctly with the expected contract, but it does not prove the real external system behaves that way in all circumstances. This is why integration strategies often include a mix of true end-to-end checks and contract-focused checks. When you operationalize integration testing thoughtfully, you reduce the number of surprises that appear only after deployment. That reduction in surprise is the real payoff. Now connect load, regression, and integration testing, because they solve different uncertainties and are strongest when combined. Regression testing protects behavior that used to work, integration testing protects the seams where systems talk to each other, and load testing protects performance and stability under stress. If you only do regression testing, you might miss an integration break that happens only when a dependency changes. If you only do integration testing, you might miss a subtle regression inside your component that does not show up in a few integration calls. If you only do load testing, you might discover performance issues but still miss functional correctness problems. Operationalizing quality is about choosing the right mix and running them at the right times, so you build confidence without wasting resources. Operators also align these tests with risk, meaning higher-risk changes get stronger and broader validation. That alignment keeps the pipeline credible because it applies effort where it matters most. When the mix is balanced, testing becomes a predictable process rather than a chaotic scramble before release. An operational lens on testing also emphasizes acceptance criteria, because tests are only useful when you can interpret results consistently. Acceptance criteria are the rules that determine whether a test result means the release is safe, needs investigation, or must be blocked. For regression and integration tests, acceptance is often binary, meaning pass or fail, but even there you need rules about retries and about distinguishing real failures from flakiness. For load testing, acceptance is often threshold-based, such as maintaining latency under a target and error rate under a limit during a sustained period. Operators are careful with criteria because criteria that are too strict can block progress for harmless noise, while criteria that are too loose allow risky releases through. Criteria also need to be stable over time, so teams do not constantly renegotiate what acceptable means. Stability helps because it turns testing into a standard, not into an argument. When you operationalize QA, you define criteria that reflect user experience and operational tolerance, not just arbitrary numbers. A key part of operationalizing QA is deciding how testing results influence pipeline decisions, because not every test needs to be a hard gate. Some results might be informational, prompting investigation without blocking a release, especially early in a program. Over time, as tests become stable and trusted, more of them can become gating checks, because the cost of ignoring them becomes too high. This gradual approach prevents the common failure mode where teams add many tests at once, create constant failure noise, then disable them in frustration. Operators also watch the feedback loop timing, because a test that takes hours to run might be valuable, but should be scheduled appropriately so it does not slow down every change. That is why layered strategies work well. Quick checks run frequently, deeper checks run less frequently, and major release gates include the full suite. Beginners can remember this as matching test cost to test value and matching test frequency to change risk. When you match those correctly, the pipeline stays fast enough to be used, while still building confidence. Testing strategy also has a security impact because failures can indicate not only bugs, but also risky behaviors, such as unexpected data exposure or unsafe error handling. Integration tests can validate that authentication and authorization rules are applied correctly across service boundaries. Regression tests can ensure that security controls remain in place and do not get accidentally bypassed. Load testing can reveal denial of service susceptibility or resource exhaustion patterns that attackers could exploit. Operators therefore treat QA not as separate from security, but as part of security posture, especially in automation-heavy environments. This does not mean every test is a security test, but it does mean that quality failures can become security incidents when they affect availability or data handling. When pipelines integrate testing with scanning and policy checks, the system gains multiple layers of defense. For beginners, the key idea is that reliability and security reinforce each other because both require predictable behavior under stress. Testing is one of the strongest ways to validate predictability. To close, operationalizing QA testing with load, regression, and integration strategies is about building confidence through repeatable evidence, not through hope and last-minute heroics. Load testing measures stability and performance under stress, revealing bottlenecks and degradation patterns that functional checks miss. Regression testing preserves known good behavior, catching breakage close to the change that introduced it and preventing slow drift into unreliability. Integration testing validates that components still cooperate correctly, protecting the seams where the most expensive failures often occur. When you combine these strategies with clear acceptance criteria, thoughtful scheduling, and stable execution environments, testing becomes a dependable release control rather than a chaotic obstacle. The operator mindset is to match test type to uncertainty, match test frequency to risk, and treat results as evidence that guides safe decisions. When you can explain what each strategy proves and why it matters to real users and real operations outcomes, you are ready to use QA as a powerful tool for safer automation at scale.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.